So, as she said, I'm Alejandro Varela from Varela Labs and Computational Science Lab. I'm doing an industrial PhD program, which basically joins together academia world and industrial world. My PhD supervisor is Gianni De Fabritis, which I think some of you already know. So yeah. Also, I realized yesterday that most people in this conference are chemists. I'm a biologist, so some of the content that you are about to see might hurt your feelings, okay? Just a second. Oh, it's a PDF, maybe. Oh, okay. So maybe this side better. Okay. So in the post-prediction challenge, what we did was, as some other people did, just exploit the structural knowledge that you can find in pdb.com, right? And so, as usual, we started searching for homologs. There was a bunch of them, I don't know, 100 something. We searched for ligands, which were crystallized there, which were similar to the ones that we have to dock. And then we developed this program called a Skeledoc, which is kind of maximal common superstructural-like, but with some improvements. And then we did some ND on top. This is the result of Skeledoc. The laser is this one. Okay, so you can see that, I think the template is the one showing transparent texture, and the query ligand is the one on top, of course. Well, I can explain later more, but you can already realize that we are mapping here a not ring element to a ring. This is kind of dangerous, but well, we wanted to try that, right? So how does the Skeledoc work? Basically, we start doing a graph comparison with a maximum click algorithm, which results in something like this, okay? You can see here that we have an oxygen atom and a nitrogen atom, and most MCS approaches, maximal common structural approaches, like the ones that you can find in RDKit, will stop here, right? This is what they will return. They will find this mapping. And all this stuff, which is identical, they won't be able to find it. So we added this auto-completion step, which basically identifies semi-completed dihedral, so 3 atoms which are continuous, and the one which is free. And it tries to map the free atom to the possibilities that the template offers. In this case, it's just this one, right? And then you repeat the process until you run out of atoms, in this case, until this point. And you can see now that this is nicely aligned. So basically, in this way, you can circumvent scaffold hopping, right, to some point. And then another nice thing, I think, is that we have this tethering part, which goes at the end once you have the mapping. So this stuff goes here, this stuff goes here. You can set a force and say, okay, I want to run a little, I think it's like a simulation with RDKit. I want to set a force of 100 going from this point to this point. And you can get like the exact same position, right? If you go here, you can see that we can just put the equivalent atoms in the same position. And I think this was key because it basically denoisifies the structures, right? So if you have a scoring function, usually they are based on distances. So if you put an aromatic ring like this, and then you put it, and the other docket post-it is like this, you are going to have different scores just because of that, right? So you have a lot of noise, which this thing can get rid of, hopefully. And then we have, then Skeledoc did his job. We wanted to minimize it a bit and let some ND on top to relax the structures and also to check if the ligand would stay on place or not. So in our company, we have developed HTMD and ASMD. So HTMD is a Python environment to set up proteins and ligands for simulation in an easy way, which is open source, by the way. So if you want to take a look, you are very welcome to do it. And ASMD is just some MD engine which runs on GPUs, and it's very fast. So we wanted to try that. So yeah, we just after Skeledoc, we minimized with ASMD. I think it was 500 steps, and then some 3 nanoseconds of equilibration. So after equilibration, you have I don't know, hundreds of frames, right? Hundreds of potential poses from which you have to choose. So we discarded the first half, and from the second half, we pick as the final pose the one which was closest to the result of the Skeledoc, right? So in this way, you have relaxed the system a bit, but you have not lost all the information that you got from the crystal structures. So these are the results. This is the metric that got us the best ranking. So this is the one that you showed to your boss, okay? But it depends a bit, right? Some other configurations put us 12, so, but overall it was a nice result. So yeah. Okay, so in the affinity prediction challenges, yeah, better this way maybe. In the affinity prediction challenges, we use a combination of Skeledoc and KDeep. So KDeep is a neural network, a 3D convolutional neural network developed by some of my colleagues. You can imagine it that as a grid. So you have the protein and the ligand co-crystallized. This is very important. It has to be co-crystallized because we use PDB-bind to train it. So this was trained on crystals, okay? This is an important fact. And yeah, so 3D convolutional network, you featureize the protein pocket and the ligand just with some grid, basically. I think we use 4 channels for the ligand, like aromatic, hydrophobic, hydrogen bond donor, and acceptor. So the usual stuff that other people use. And yeah, and then we have just skeledocket all the ligands in the challenge. And we just use this application, right, which is available in playmolecule.com for free for everybody. We will do a little demo afterwards. And this is how we ranked. This is a stage 2 in both cases. So this is free energy prediction and this is ligand scoring. So the results were nice. We actually tried in stage 1 for base. Instead of KDeep, we use delta-delta, which is just another application using convolutional neural networks. But this delta-delta tries to predict the relative free energy of binding, right? But probably I just included some ligands which were not close enough. And at the end, the results were positively correlated, but just the candle stop was 0.1. So not very good. So yeah. And now I'm going to talk a bit about the sample 6 challenge, which my colleague Boris Satarov worked in. He couldn't make it, so I'm just showing a bit his results for him. So if you have any questions, just contact him. I think he will be very glad to answer you. Basically, what he did was he took some label data with log P information from the EPICAL dataset. He removed those which had a Tanimoto coefficient under 0.05, and then he ended up with these 12,000 something compounds. In order to featureize, he used several fingerprints and features from our kit, like molecular weight, cheese, and so on and so forth. And then he just used extreme gradient using trees-based method. I think some other somebody yesterday talked about this method, which was popular among the top performing contestants. And he ranked second out of 90 other people with very nice RMSE and R square. So yeah, I want to talk a bit about the usual problems that I encountered doing this, and in general, I think in the field, which is one of them is just converting between formats. This is something that can drive me very nuts. I mean, you can lose bond information, you can lose charges information. Right now, what I'm doing is just trying to keep my RTKit molecule instance and then write from there instead of using OBubble. But if anybody has a suggestion, I will be glad to hear it. Also, signing charges and partial charges, I think this is something that there is not a very good open source software to do it. But yeah, if somebody knows, so perfect. And then chemistry in general, when we started the challenge, we just had a little, so in the steps that I show right here in Skeledoc, we just had this step. But this step was not even prepared for microcycles, so fused rings. So we spent a lot of time trying to develop that and adapting it for the challenges, query ligands. Now it works a bit better, at least. Yeah, I would say it works better. And yeah, I want to show. Also, that's one of the reasons why we perform a bit badly in cats. I think because there were fused rings, right, which at the time we couldn't handle very well. So the poses look a bit not very good, right? Then we redid it after after the results were published with the new code, and it works better. So we got now a candle stop 0.3, sometimes 0.25. So at least it's positive correlated. The manual supervision, I think somehow we have to get rid of this. I don't know. I was really hoping that convolutional neural networks would be able to re-rank poses so that the best one would be on top. Apparently, this is not so easy. I think Ragosa is working on this with some success, but I think it's still not as good as Bina. So yeah, still a lot of work to do. And then something that we in Accelera we are really worried about is how to systematically use previous affinity knowledge, right? In cats, for example, I think in Camel there was a lot of affinity data, but we don't know how to use it because with KDeep we were trying to build a retrainable KDeep, but this is not straightforward. Also, there is a lot of batch effects in public databases, affinity points, and yeah. So not very trivial. So this is our platform, playmolecule.com, where we put the apps that we develop. So yeah, we have several ones. I like to think about it as Google Play Store for bioinformatics software, more or less. And if some of you are interested in develop an app, that we will very glad to put it here. It would be nice to test if some outsider is able to put his stuff here using our previous templates. Yeah, that would be awesome. And well, if we can we try to put the demo?
Yeah, so you'll have to run it.
So okay, yeah, I just want to show. It should be already run.
Right.
Yeah. Okay, can you, yeah, like this? Okay. Yeah, okay. So you can see here, this is our platform. These are actually the query ligands in the challenge for cats. And you can see here that we have the template. Okay, this is the template. And here we have docked all the, come on. We have docked several ligands on top. And you can see here that in the app, we don't even use like a very high tethering force. But if you use a higher force, you can get all these rings exactly in the same position. The problem is that if you use a very high tethering force, then the chirality gives a bit of troubles. We are still handling that. But yeah, ideally, we will get rid of those problems. And yeah, this is available for everybody. Maybe if the new challenge fits the use case of Skeledoc, you can give it a try. And yeah, tell us how you feel about it. And then just to finish. Oh, sorry. Yeah, my bad. Well, that's my just was just the last. Yeah, it was. I want to thank the organizers. I think these challenges are amazing. I think they really. I mean, they can tell us better which softwares beats who, right? Otherwise, it's just impossible. If you search the literature, every software beats the other software, so it's impossible to get a grasp on what's really working and not. For example, I discovered the ICM docking, which I have never heard about, and I think it's amazing. I don't know. I mean, trying to just dock the aspects diverse set doesn't prove much, right? So these challenges are very important. And yeah, I want to thank my colleagues at Celera and Computational Science Lab, particularly David Sabadin, which was my supervisor during this challenge, Alberto Cusolini and Gerard Martinez for building the app, and of course my supervisor Gianni Fabritis for giving me the opportunity to work there, and of course to the audience for his attention. Okay, thank you. Go ahead. Yeah, okay.
Oh, not that, the mic.
Oh, the mic, okay,
Sorry.
sure. Yeah.
I was sure it's for the at-home listener. Thanks. Oh, thanks.
Very cool work. I was just wondering if you were able to use like KD, which predicts KDs directly, with delta delta, which predicts delta, free energy differences. Can you use them in some sort of thermodynamically consistent way to improve your performance? Can you use your KD and delta delta models in a way that's thermodynamically consistent to achieve more than just using one tool to predict? So something more accurate by fusing the data together.
So I like to think about these things in you have to use it in a black box manner. I just actually what I did was once I had the poses, I just sent it to KD pap in play molecule. That's it. I think this is the way to go, right? I didn't check for more thermodynamical consistency or anything. I mean, it would be nice, right? Maybe use the MD that I have generated to check maybe for a correlation with the KD results. If that was your question, try to check for consistency between the KD prediction and a more thermodynamics-based method.
Well, one of them gives you a delta G, and the other one gives you a delta delta G. And if you're making multiple predictions, you have thermodynamic consistency that should be obeyed. And so maybe there's a way to use that, like they do free energy calculations by a maximum likelihood.
Yeah, it could be, but I haven't tried that. No. Yeah. Also, that didn't work that well. I saw yesterday. Some speaker told about that you need somehow a Tanimoto coefficient greater than 0.4 to get QSAR models work a bit nicely. And I for sure included something which was not on that scope. So maybe that could explain it. Yeah. Thanks.
Since KDeep is using binding poses, have you guys looked at the use of test time augmentation, like taking the actual pose, rotating, cropping it like they do in CompNuts all the time to see if you can then, let's say, average your 10 predictions to get a better one? And have you looked at the use of dropout during test time as well to see if you can actually get calibrated error bars for the predictions off KDeep?
We did try to do some data how do you call it? Data enhancement? Yeah, data augmentation, yeah, true. We did rotate the poses a bit and the protein, but yeah, I mean, of course that helps, right? But what I would really like to try was to maybe skeledoc the affinity data that you have in Campbell, so the ligands that you have in Campbell, and include that on the training set. I think that would help a bit, maybe. Yeah, we should try more of these techniques, right? Maybe just poses of the crystal instead of the crystal directly. I don't know, something like this. Yeah. And then regarding the dropout, yes, I think my colleague used dropout during training. So yeah.
No, I mean during when you're making your prediction.
No, that's not. No, that we didn't do that. No problem.